Many people probably have heard of string theory. You may have heard something about what it's about. You may even have heard that there's some degree of controversy about whether it counts as doing proper science or not. So, basically what I'm going to try and tell you today is why we want to spend any time thinking about this. And to do that, I need to tell you a bit about theories of everything. Now this is the ultimate pipe dream of theoretical physics. We want to write down one spectacular set of mathematical equations that will, at least in principle, describe everything that will ever happen in the universe at the most fundamental level. Sounds a bit ambitious. So, the first question you might ask is, why would we try and do such a thing? We already have two theories that between them describe every experiment we've ever done. So these are gravity, which tells us about very big things. It tells us how planets orbit stars, how apples fall on famous scientists' heads, and so on. And we have quantum mechanics, which describes the world at the very smallest level. It says how the different particles are going to interact with each other. But there are some situations where we would actually need both of these things. You can have circumstances where there's very, very strong gravity, but coming from a matter source which is in a really, really confined space. So, for instance, this is the centre of this is a black hole. So in the centre of a black hole, or for instance the beginning of the universe, you have essentially infinitely dense matter. Okay, and in this circumstance you need to use both gravity and quantum mechanics, and as it turns out, they break. Completely, totally nonsense when you do this. Every answer you get is infinity. And that's not very helpful for doing physical predictions. So, what a theory of everything is meant to do is it's meant to reconcile these two theories. It's meant to say, we're going to zoom in really closely, look at gravity as closely as we possibly can, and still get finite answers out. This is the idea. Okay, and I'm telling you a lot about how sort of physical equations can break when you look at them at a different scale, and that might be a surprise. You might think an equation is an equation and it has to work all the time. But actually that's not true, so let's see an example. Here is a river. This is described by fluid dynamics. We use sensible physics that uses sensible everyday variables. We talk about the rate of flow of the river, the pressure of the water, the temperature, things like this. But if we were to think about zooming in on this picture, zooming in so closely that we can see the individual molecules in the water, we have a picture like this. We can try and ask the same questions. We can say, how hot is this? How thick is this? What pressure is this at? And really those questions, you realise quite quickly, are just nonsense now. They don't make any sense. We have to use different physics to describe this situation. And we can keep going and find that these are not really billiard balls crashing into each other. They have some internal structure. We have oxygen and hydrogen atoms. And the interactions now require quantum mechanics to describe them. So what we've seen is even if we understand the large-scale picture very well, in this case fluid dynamics, if we zoom in very closely, there's no guarantee that the picture we're left with will actually make any sense. So we need to pick some different physics to describe the smaller scale situation. And this is what string theory is going to do for gravity. So, what's the idea? String theory simply fixes this small-scale problem by turning the smallest particles in the universe from dots, just things with no size at all, into tiny little loops of string, so small that we cannot possibly observe them directly at the moment. So this is what it does, but we also need to get all the different kinds of particle out. There's only one type of string, there's lots of particles, electrons, protons, etc. And the analogy here is very much like with music. If you're listening to a guitarist or something, the string he's playing can vibrate at different frequencies, it has different harmonics, and you interpret that as different notes that you hear. In physics, again, the string can vibrate with different harmonics, but this time the different harmonics mean different kinds of particle. So for instance, if it vibrates more vigorously, this means the string will be heavier. And the analogy actually goes further than this. So if we imagine zooming our picture of a string out so that we can't really see its finite size anymore, we can't see the fact that it's vibrating, but we're certainly aware of it because we observe a different kind of particle. Again, this is similar to what's happening in music. If you try and watch a guitarist playing, you will not see the different harmonics of the string. You can't pick them out with your eyes, but you certainly know that they're there because you hear different notes. Okay, so this is the basic idea of string theory. And now the question you might ask is, well, what does that mean? This, unfortunately, is rather a fair representation of the extent of our answer at the moment. So what I'm going to do is I'll just give you some basic pros and cons of the theory, and you can sort of decide whether you think it looks sensible. So first, the pros. The most important thing, the most important question you answer is, did it solve our problem? Did we manage to make gravity and quantum mechanics work together? And the answer is yes, as it turns out. String theory is a fully consistent theory of everything. All of these answers are finite, it makes sense at any energy scale, length scale, sorry. And more than that, when we zoom out, so that we're no longer aware that the string has this finite size, all of the physics we know and, well, love in some people's cases, at least, is reproduced. So it works, it does everything that we wanted it to. But it should do more than that. In order to be a scientific theory, we need to be able to confront it with an experiment. We need to say, this is my prediction, this is what the experiment said, was I right? Was string theory nonsense? And in principle, at least, it does this. It would have to, because we know it works in exactly the situation where our previous theories didn't. So there are calculations we can do that give a different prediction to what we had before. There's also this rather, woolly idea that somehow the mathematical beauty of the theory should be a good way of determining that it's got anything to do with the world. There's definitely a philosophical argument to be had there about whether that's a reasonable way of doing physics, but it has actually turned out to be a useful guiding principle many times in the past, so physicists are kind of inclined to stick with it. And sort of the reason why it's so beautiful is that it's unique in the sense that once I decide that the universe should be made of tiny little strings, that's the only choice I had. Everything else about the theory is completely fixed, and this is in stark contrast to more or less everything else that we ever do in sort of any academic endeavour, I think. Certainly in physics. Unfortunately, this uniqueness causes a few problems. So the biggest of these, and the one that people find the most unpalatable about string theory, is the fact that it tells us we should be living in 10 dimensions. Okay, so most of you are probably pretty happy with the fact that the world is 3-dimensional. And a lot of you will probably have heard some physicists banging on at you in the past about how you should think about time as another dimension, and therefore there's really 4. And maybe you're quite uncomfortable with that, but you can at least sort of buy it, because time is something you experience. It's definitely there, even if thinking about it as another dimension is a bit strange. Unfortunately, these other 6 have no such intuitive crutch to lean on. They bear no resemblance to any human experience of the world. So, the theoretical physicist's get-out clause here is to use scales, again, as an excuse, basically. We say, well, we're already prepared to believe that the string is so small we can't see it's a string. Why don't we also believe that the dimensions are so small we can't see them? Okay. The problem with this is that, of course, the string can see them because it's so much smaller. And the way that the string experiences the different colored dimensions changes the physics that we observe in a really, really big way. And that's bad because we don't understand the maths involved in how its spaces curl up whatsoever. So this is an attempt at drawing a 6-dimensional space on a 2-dimensional projector. It doesn't work for a relative to it justice. But yeah, essentially we don't understand the maths, which means that we can't make any real predictions that depend on how this space is curled up. And that means it's very hard to put anything out there that we could test against experiments. And so one reason why it's difficult to test, sort of the bigger problem, is that even doing it, building a machine that's big enough and powerful enough to see down this far, essentially building the biggest microscope in the universe, would require us to build a particle accelerator that really makes the Large Hadron Collider look pretty small, to the extent that even in our wildest Star Trek-y fantasies, it's not going to happen because it's going to have to be the size of the entire galaxy, with current technology. So it's fair to say that this is not going to happen. Yeah, so these are sort of the pros and cons. To sum up, I will defer to minds that are much greater than my own. So this is one of the greatest physicists to ever lived, Richard Feynman. And he would not have enjoyed string theory very much. He's very much of the practical view that the one and only thing your physics has to do is agree with the experiment. Everything else is besides the point. All of this stuff about beauty is just woolly nonsense, and physicists are wasting their time thinking that way. And he's of course right, and string theorists certainly need to be aware that they should be spending more time trying to make experimentally verifiable predictions from their theory. Okay. But to close on an optimistic note, is a point due to one of our professors in Cambridge. Basically what he is saying is that string theory does appear to be a completely consistent theory of everything. That is amazing as a physical theory. It's the only one we've got that is even remotely plausible. And as such, as physicists, we're almost duty-bound to try and study it. And that's where I'll stop. Thank you.
Thanks so much, Andrew. Question? Bonus questions, if we have any questions from our students. So, just curious, sometimes I also heard about like the 11th dimension, so that may be fundamentally different.
Yeah, it's sort of, when I say that string theory is unique, I sort of slightly lie, only very slightly. There's 5 different variants, and one of them says that you live in 11 dimensions, in fact, and they should all be kind of linked together in some really extremely complicated way. But that, I think, is something I don't want to go into.
What are the other dimensions?
Where?
Sorry.
So, indeed, you can't look in these dimensions, of course, you can't see them, but the idea basically is if you could get an experiment that's somehow powerful enough to see down to the length scale of the bottom, then you would be able to see them like any other dimension. However, to give you a feeling of what these length scales are, the naive estimate at the moment for the length of a fundamental string is about 10 to the minus 35 meters. That's 1 divided by 1 with 35 zeros after it. So to put that in context, a grain of flour is about 10 to the minus 5 meters. So if I scale the string up such that it's 1 meter long, okay, just imagine doing that, then if I scale the grain of flour in the same way, it'll fill up the entire universe. So we're really quite a long way away from ever getting anywhere near observing these extra dimensions.
Can I ask, how string theory came to decide there were 10 rather than 8 or 12?
Now, that's quite a technical question to answer properly, I'm afraid. So it should be that the string moving around in space should obey the laws of relativity. So things should be true, like the speed of light should be constant, regardless of how I look at it. And it so turns out that if you suppose that the light is made of strings, this is only true if it lives in exactly 10 dimensions. Not any other.
Can I ask them why it is strings instead of cubics? Is there any reason it is called string?
Yeah, so that's a good point. You might think if you're living in 3 dimensions that the most natural thing to extend a point to would be a blob, right? It should be a 3-dimensional thing itself. The reason is really this thing about harmonics. If you look at the different things you get out of a string, you get a discrete collection of possible different particles. If you were to look at the things you get out of a blob, you'll get a continuous spectrum. There'll be infinitely many different possibilities. And we know there are not infinitely many different kinds of particles in the universe. So this is why you end up having to look at the string.
One last question.
There are many skeptics of string theory, and you've presented some good reasons for that. Is that their only reasons, or are there any competing theories?
There are some different theories. So it's fair to say that string theory is the only real theory of everything around at the moment. There are other theories that seek to make quantum and gravity work together. They actually take a much more extreme hypothesis than probably anything I said in this talk, in that they suppose that space, instead of being a continuous thing, should be broken down into like a discrete lattice kind of thing. And they are even harder to make experimental predictions with than string theory, and even less well understood mathematically. So at the moment, strings are considered to be the best possibility.
Okay, point. Start having a sore head. Sure. Move on. Thanks very much, Andrew.